In mathematics, Big O notation describes the limiting behavior of a function when the argument tends towards a particular value or infinity, usually in terms of simpler functions. It is a member of a larger family of notations that is called Landau notation, Berkman Landau notation, or asymptotic notation. In computer science, Big O notation is used to classify algorithms by how they respond to changes in input size. In analytic number theory, it is used to estimate the error committed while replacing the asymptotic size, or asymptotic mean size, of an arithmetical function by the value, or mean value, it takes at a large finite argument. A famous example is the problem of estimating the remainder term in the prime number theorem. Big O notation characterizes functions according to their growth rates. Different functions with the same growth rate may be represented using the same O notation. The letter O is used because the growth rate of a function is also referred to as order of the function. A description of a function in terms of Big O notation usually only provides an upper bound on the growth rate of the function. Associated with Big O notation are several related notations, using the symbols O, omega, and theta, to describe other kinds of bounds on asymptotic growth rates. Big O notation is also used in many other fields to provide similar estimates. Formal definition. Let f and g be two functions defined on some subset of the real numbers. One writes if and only if there is a positive constant m such that for all sufficiently large values of x, the absolute value of f is at most m multiplied by the absolute value of g. That is, f equals O, if and only if there exists a positive real number m and a real number x0 such that, in many contexts, the assumption that we are interested in the growth rate as the variable x goes to infinity is left unstated. And one writes more simply that f equals O. The notation can also be used to describe the behavior of f near some real number a. We say if and only if there exist positive numbers delta and m such that, if g is non-zero for values of x sufficiently close to a, both of these definitions can be unified using the limit superior, if and only if. Additionally, the notation O is also used to denote the set of all functions f that satisfy the relation f equals O. In this case we write, example, in typical usage, the formal definition of O notation is not used directly, rather, the O notation for a function f is derived by the following simplification rules. If f is a sum of several terms, the one with the largest growth rate is kept, and all others omitted. If f is a product of several factors, any constants are omitted. For example, let f equals 6 by 4 minus 2 by 3 plus 5, and suppose we wish to simplify this function, using O notation, to describe its growth rate as x approaches infinity. This function is the sum of three terms, 6 by 4, minus 2 by 3, and 5. Of these three terms, the one with the highest growth rate is the one with the largest exponent as a function of x, namely 6 by 4. Now one may apply the second rule. 6 by 4 is a product of 6 and x4 in which the first factor does not depend on x. Omitting this factor results in the simplified form x4. Thus, we say that f is a Big O of. Mathematically, we can write f equals O. One may confirm this calculation using the formal definition. Let f equals 6 by 4 minus 2 by 3 plus 5 and g equals x4. Applying the formal definition from above, the statement that f equals O is equivalent to its expansion. For some suitable choice of x0 and m and for all x greater than x0. To prove this, let x0 equals 1 and m equals 13. Then, for all x greater than x0. So usage. Big O notation has two main areas of application. In mathematics, it is commonly used to describe how closely a finite series approximates a given function, especially in the case of a truncated Taylor series or asymptotic expansion. In computer science, it is useful in the analysis of algorithms. In both applications, the function g appearing within the O is typically chosen to be as simple as possible, omitting constant factors and lower-order terms. There are two formally close, but noticeably different, usages of this notation: infinite asymptotics and infinitesimal asymptotics. This distinction is only in application and not in principle. However, the formal definition for the Big O is the same for both cases, only with different limits for the function argument. Infinite asymptotics Big O notation is useful when analyzing algorithms for efficiency. For example, the time it takes to complete a problem of size n might be found to be t equals 4n2 minus 2n plus 2. As n grows large, the n2 term will come to dominate, so that all other terms can be neglected. For instance, when n equals 500, the term 4n2 is 1000 times as large as the 2n term. Ignoring the latter would have negligible effect on the expression's value for most purposes. Further, the coefficients become irrelevant if we compare to any other order of expression, such as an expression containing a term n3 or n4. Even if d equals 1,000,000 n2, if u equals n3, the latter will always exceed the former once n grows larger than 1,000,000 equals 1000, 0003 equals u. Additionally, the number of steps depends on the details of the machine model on which the algorithm runs. But different types of machines typically vary by only a constant factor in the number of steps needed to execute an algorithm. So the Big O notation captures what remains. We write either or and say that the algorithm has order of n2 time complexity. Note that equals is not meant to express is equal to in its normal mathematical sense, but rather a more colloquial is. So the second expression is technically accurate while the first is considered by some as an abuse of notation. Infinitesimal asymptotics Big O can also be used to describe the error term in an approximation to a mathematical function. The most significant terms are written explicitly, and then the least significant terms are summarized in a single Big O term. Consider, for example, the exponential series and two expressions of it that are valid when x is small. The second expression means the absolute value of the error x minus is at most some constant times x3 when x is close enough to 0. Properties. If the function f can be written as a finite sum of other functions, then the fastest growing one determines the order of f. For example, in particular, if a function may be bounded by a polynomial in n, then as n tends to infinity, one may disregard lower-order terms of the polynomial. Another thing to notice is the sets O and O are very different. If c is greater than 1, then the latter grows much faster. A function that grows faster than nc for any c is called superpolynomial. One that grows more slowly than any exponential function of the form Cn is called subexponential. An algorithm can require time that is both superpolynomial and subexponential. Examples of this include the fastest known algorithms for integer factorization and the function n log n. We may ignore any powers of n inside of the logarithms. The set O is exactly the same as O. The logarithms differ only by a constant factor equals c log n, and thus the Big O notation ignores that. Similarly, logs with different constant bases are equivalent. On the other hand, exponentials with different bases are not of the same order. For example, 2n and 3n are not of the same order. Changing units may or may not affect the order of the resulting algorithm. Changing units is equivalent to multiplying the appropriate variable by a constant wherever it appears. For example, if an algorithm runs in the order of n2, replacing n by cn means the algorithm runs in the order of c2n2, and the Big O notation ignores the constant c2. This can be written as c2n2 equals O. If, however, an algorithm runs in the order of 2n, replacing n with cn gives 2cn equals n. This is not equivalent to 2n in general. Changing variables may also affect the order of the resulting algorithm. For example, if an algorithm's runtime is O when measured in terms of the number n of digits of an input number x, then its runtime is O when measured as a function of the input number x itself, because n equals O. Product sum this implies, which means that is a convex cone. If f and g are positive functions, multiplication by a constant let k be a constant. Then, if k is non-zero, multiple variables. Big O can also be used with multiple variables. To define Big O formally for multiple variables, suppose n are two functions defined on some subset of, we say if and only if. Equivalently, the condition that for some can be replaced with the condition that, where denotes the Chebyshev distance. For example, the statement asserts that there exist constants c and m such that where g is defined by, note that this definition allows all of the coordinates if to increase to infinity. In particular, the statement is quite different from. This is not the only generalization of Big O to multivariate functions, and in practice, there is some inconsistency in the choice of definition. Matters of notation. Equals sign. The statement, f is O, as defined above is usually written as f equals O. Some consider this to be an abuse of notation, since the use of the equals sign could be misleading as it suggests a symmetry that this statement does not have. As De Bruijn says, O equals O is true but O equals O is not. Nuth describes such statements as one-way equalities, since if the sides could be reversed, we could deduce ridiculous things like n equals n2 from the identities n equals O and n2 equals O. For these reasons, it would be more precise to use set notation and write FO, thinking of O as the class of all functions h such that h, c, g for some constant c. However, the use of the equals sign is customary. Nuth pointed out that mathematicians customarily use the equals sign as they use the word eyes in English. Aristotle is a man, but a man isn't necessarily Aristotle. Other arithmetic operators. Big O notation can also be used in conjunction with other arithmetic operators in more complicated equations. For example, h plus O denotes the collection of functions having the growth of h plus a part whose growth is limited to that of f. Thus, expresses the same as example. Suppose an algorithm is being developed to operate on a set of n elements. Its developers are interested in finding a function t that will express how long the algorithm will take to run in terms of the number of elements in the input set. The algorithm works by first calling a subroutine to sort the elements in the set and then perform its own operations. The sort has a known time complexity of O, and after the subroutine runs the algorithm must take an additional 55n, 3 plus 2n plus 10 steps before it terminates. Thus the overall time complexity of the algorithm can be expressed as t equals 55n 3 plus O. Here the terms 2n plus 10 are subsumed within the faster growing O. Again, this usage disregards some of the formal meaning of the equals symbol, but it does allow one to use the Big O notation as a kind of convenient placeholder. Declaration of variables. Another feature of the notation, although less exceptional, is that function arguments may need to be inferred from the context when several variables are involved. The following two right-hand side Big O notations have dramatically different meanings. The first case states that f exhibits polynomial growth, while the second, assuming m greater than 1, states that g exhibits exponential growth. To avoid confusion, some authors use the notation rather than the less explicit multiple usages in more complicated usage. O can appear in different places in an equation, even several times on each side. For example, the following are true for the meaning of such statements is as follows. For any functions which satisfy each O on the left side, there are some functions satisfying each O on the right side, such that substituting all these functions into the equation makes the two sides equal. For example, the third equation above means For any function f equals O, there is some function g equals O such that nf equals g. In terms of the set notation above, the meaning is that the class of functions represented by the left side is a subset of the class of functions represented by the right side. In this use, the equals is a formal symbol that, unlike the usual use of equals, is not a symmetric relation. Thus, for example, no equals O does not imply the false statement O equals no orders of common functions. Here is a list of classes of functions that are commonly encountered when analyzing the running time of an algorithm. In each case, C is a constant and n increases without bound. The slower-growing functions are generally listed first. The statement is sometimes weakened to derive simpler formulas for asymptotic complexity. For any n is a subset of for any, so may be considered as a polynomial with some bigger order. Related asymptotic notations. Big O is the most commonly used asymptotic notation for comparing functions, although in many cases Big O may be replaced with big theta for asymptotically tighter bounds. Here, we define some related notations in terms of Big O, progressing up to the family of Berkman-Landau notations to which Big O notation belongs. Little o notation. The informal assertion, f is little o of g, is formally written f equals O, or in set notation fo. Intuitively, it means that g grows much faster than f, or similarly, that the growth of f is nothing compared to that of g. It assumes that f and g are both functions of one variable. Formally, f equals O, as n infinity means that for every positive constant epsilon there exists a constant n such that. Note the difference between the earlier formal definition for the Big O notation and the present definition of little o. While the former has to be true for at least one constant m, the latter must hold for every positive constant epsilon, however small. In this way, little o notation makes a stronger statement than the corresponding Big O notation. Every function that is little o of g is also Big O of g, but not every function that is Big O of g is also little o of g. If g is non-zero, or at least becomes non-zero beyond a certain point, the relation f equals O is equivalent to, for example, little o notation is common in mathematics but rarer in computer science. In computer science, the variable is most often a natural number. In mathematics, the variable and function values are often real numbers. The following properties can be useful. 4. As with Big O notation, the statement is usually written as, which some consider an abuse of notation. Big Omega notation. There are two very widespread and incompatible definitions of the statement where a is some real number, infinity, or minus infinity, where f and g are real functions defined in a neighborhood of a, and where g is positive in this neighborhood. The first one is used in analytic number theory, and the other one in computational complexity theory. When the two subjects meet, this situation is bound to generate confusion. The Hardy-Littlewood definition in 1914. G.H. Hardy and J.E. Littlewood introduced the new symbol, which is defined as follows. Thus is the negation of. In 1916 the same authors introduced the two new symbols are thus defined. Hence is the negation of, and the negation of, contrary to a later assertion of D.E. Nuth. Edmund Landau did use these three symbols, with the same meanings, in 1924. These Hardy-Littlewood symbols are prototypes, which after Landau were never used again exactly thus. Became. These three symbols, as well as, are now currently used in analytic number theory. Simple examples we have and more precisely however the Nuth definition in 1976. Donald Nuth published a paper to justify his use of the symbol to describe a stronger property. Nuth wrote, "For all the applications I have seen so far in computer science, a stronger requirement is much more appropriate." He defined with the comment, "Although I have changed Hardy and Littlewood's definition of, I feel justified in doing so because their definition is by no means in wide use. and because there are other ways to say what they want to say in the comparatively rare cases when the definition applies. However, the hardy little word definition had been used for at least 25 years. Family of Berkman-Landau notations. Aside from the Big O notation, the big theta theta and big omega omega notations are the two most often used in computer science. The small omega omega notation is occasionally used in computer science. Aside from the big O notation, the small o, big omega omega and notations are the three most often used in number theory. The small omega omega notation is never used in number theory. Use in computer science informally, especially in computer science. The big O notation often is permitted to be somewhat abused to describe an asymptotic type bound where using big theta theta notation might be more factually appropriate in a given context. For example, when considering a function t equals 73n3 plus 22n2 plus 58, all of the following are generally acceptable, but tighter bounds are usually strongly preferred over looser bounds. T equals O, T equals O, T equals theta. The equivalent English statements are respectively: T grows asymptotically no faster than n100, T grows asymptotically no faster than n3, T grows asymptotically as fast as n3. So while all three statements are true, progressively more information is contained in each. In some fields, however, the big O notation would be used more commonly than the big theta notation. For example, if t represents the running time of a newly developed algorithm for input size n, the inventors and users of the algorithm might be more inclined to put an upper asymptotic bound on how long it will take to run without making an explicit statement about the lower asymptotic bound. Extensions to the Bachmann-Landau notations and other notations sometimes used in computer science is O. F equals O is shorthand for F equals O logkg for some k. Essentially, it is big O notation, ignoring logarithmic factors because the growth rate effects of some other super-logarithmic function indicate a growth rate explosion for large-sized input parameters that is more important to predicting bad runtime performance than the finer point effects contributed by the logarithmic growth factor. This notation is often used to obviate the nitpicking within growth rates that are stated as too tightly bounded for the matters at hand for any constant k and any epsilon greater than 0. Also, the L notation, defined as is convenient for functions that are between polynomial and exponential in terms of